right, you guys, I haven't recorded in a really long time, so I'm trying to figure out what this looks like. Um, okay, so I hope you can see the screen for differentiation. I don't like that this is in the middle of things. I unpin, I don't know. Okay, I guess that's fine. And this icon can't be moved. Okay, so here we are, differentiation notes, fall 2023. I hope that this is what's showing up. Right now, today's date is, let's see, May 20. Okay, my chair is stuck on here. May 29th of 2023. It just so happens that I don't have this video for this first portion of this lecture. So let me just get right in here and start. So first thing, differentiation. As soon as my camera focuses, it's just the derivatives you're expected to know in this class, and you'll see them time and time again. So this notation here means the derivative of this function with respect to x. And so basically what it's saying is if you graphed this, some constant times x, what would the slope of that line be? And if you think about this, this is just like y equals mx plus b. And the coefficient of x is indeed your slope. Everywhere the slope would be the same. And so the answer to this is simply C. The constant, again, in this case, if you have the graph of a constant, so if this is the x-axis and the y-axis, and you graph y equals a constant, the slope of that, because it never rises, is always going to be just plain old, I'm sorry, the slope of it's going to be 0 because it doesn't rise at all. And so this is just a plain old 0. Okay, this one, the pattern is pretty straightforward here. You take the exponent on x, and that becomes the coefficient out front, and you multiply that by x, and then you reduce this by 1. So it's to the n minus 1 power. So it's n times x to the n minus 1 power. Okay, and then this is the same question, but this time we have u, which is a function of x. And so we have to use the chain rule in this case. And so basically what it looks like is you have n times u to the n minus 1. And at this point, everything looks the same. But the problem is u is a function of x. So then we just have to multiply by du over dx, like so. Sorry, I'm going to check. I don't like to make mistakes in my videos. Okay, it tells me I'm presenting to everyone, which I already know. Okay, and then this one, the derivative of e to the x, this is fascinating. If you graph the graph of y equals e to the x, and you want to know the slope of the line tangent to it at any point, it literally is that y value, whatever that is, if that happens to be 7, and that means that the slope of this thing right here is in fact 7. So this one is pretty easy to memorize. It's just plain old e to the x. Okay, this one, the derivative of the natural log of x is just 1 over x. And then likewise, here we use the chain rule. So this would be 1 over u times du over dx. Okay, and then the derivative of the sine. The derivative of the sine is just the cosine of x. But to help me remember that is it, I think of graphing the sine function graph. And remember, on a unit circle, the sine is just the y coordinate. So at 0 radians, the sine is 0. And then at pi over 2, the sine goes up to 1. And so you end up with this graph here. And so that is your sine. That's the graph of sine of x. And so what's nice about that is you'll notice that the slope here is positive. And this happens to be positive 1, which is exactly equal to the cosine. If you graph the cosine of x, it does like this. And so the derivative of the sine is exactly equal to the cosine of x, which I just think is really cool. Okay, so the derivative of the sine, this is minus the cosine of x. And, in this case, I'm sorry, I take that back. I'm sorry, this is the same thing. It's the cosine of u times du over dx. Okay, sorry, that's cosine of u. Sorry, I thought it was asking me for the derivative of the cosine, which is minus the sine of x. And then this one has the chain rule in it. So the derivative of the cosine of u would be minus the sine of u, but then the chain rule times du over dx. Okay, sorry, you guys, I'm just checking as I go along here. I have my notes on one screen that you can't see right now, and I just want to make sure that I have everything there. Okay, for the trig functions, there's a silly mnemonic device. I am seeking a special tangent, like a tan guy, like a tangent. Okay, why? Because. And so this stands for secant, And then the cofunction is cosecant. Again, secant, and then this is minus the cosecant, and then this is the tangent, and its cofunction is the cotangent. And so the way this works is if you want the derivative of the secant, it's the secant times the tangent. If you want the derivative of the tangent, it's secant times secant, or secant squared. And then this is the cosecant. So the derivative of the cosecant is minus cosecant times cotangent. And the derivative of the cotangent is minus cosecant squared. So the derivative of the tangent here is just secant squared of x, like so. No need for the chain rule. Technically, you could use the chain rule if you wanted to. The derivative of x with respect to x, which would just be dx over dx, which is kind of silly. That's just equal to 1. Okay, so it ends up being secant squared of x. Okay, this one is the same question, but this time we have u, and so we have to worry about the chain rule. So this would be secant squared of u, but then times du over dx. All right, the derivative of the secant is the secant times the tangent, so secant of x times the tangent of x. And in this case, same question, but with a u in there. So this would be the secant of u times the tangent of u times du over dx. Okay. All right. And something that I see sometimes, and I don't get it, is students sometimes make up a function called secant tangent of u. And you might say it that way when you're in a hurry, but there's really no such thing. It's secant of u times the tangent of u times du over dx. Okay. The derivative of the cotangent here is just minus cosecant squared of x. And then same question, derivative of the cotangent of u is minus cosecant squared of u, but then times chain rule du over dx. Okay, this is the product rule. And so this is u times the derivative of v with respect to x, and then plus v times du over dx. Okay, and because this is being added, it doesn't matter what order you do these. Some students like to do, the derivative of this times this function plus the derivative of this times this function. It doesn't matter because multiplication is commutative and addition is commutative. So there's different variations of this. I always do it the same way. I just copy down the first function and then times the derivative of the second one. And then I copy down the second function times the derivative of the first. And it doesn't really matter what form it takes. It'll be correct either way. Okay, this is the quotient rule, and there's a joke about this. We're in Colorado, so it's the low D high. Remember, you start off low, okay, because we're in Colorado. You don't want to start off high, okay? So you do low times du over dx. So it's low D high minus high D low all over low low. So that would be v squared, like so. So low D high minus high D low over low low. Okay, this question comes up so often. I'm not sure how to approach this in a way that makes sense. I guess the issue is that students sort of vaguely understand what linearization means, and then that seems to cause issues with the procedure. And so basically what's happening here is what we're trying to do is look at the natural log of, this is the function y equals the natural log of x. Okay, and what we're saying is right here somewhere, there's a 3, and the question is we want to know what is that y value right there. So that would be the natural log of 3. Okay, it's asking me if I'm still here, so I want to stay in the call. So the question is, what is that? So the problem is, without a calculator, we need to rely on some other method. And so what you can do is think about this function at some value of x that's close to 3, that's convenient. And I think that the most convenient value would be to try x equals e, which is about 2.7. So we know that e is 2.7, so that we can estimate exactly. So if we go to e here nearby, we know that this y value is equal to the natural log of e. But by definition, the natural log of e is what power do you put on there to get e? Okay, the base e is what? And that would just be 1. So we know that this is 1, that the natural log of e is just 1, because e to the 1 is equal to E. Okay, so what we do here is we take this point here at E comma 1, and we do a tangent line to it. What is the equation of the tangent line? And for values very, very close, we will get, if we stay on the line, though it's not curved like the natural log function is, it'll give us a good estimate of the value of the function at 3. So all we really need to do is figure out the equation of this line, and we're set. To get the equation of a line, all you need to know is the slope and 1 point on the line, and we have that. So we have 1 point on the line. We just need to get the slope. But we already talked about this. The derivative of the natural log, that would tell us the slope is just 1 over x. So the derivative of the natural log of x with respect to x is just 1 over x. So if we want to evaluate this at x equals 3, the derivative is 1/3, but we're interested in this nearby point at which we're going to draw this tangent line. So if we evaluate this at x equals e, we end up with 1 over e is equal to the slope m. So what that's saying is the slope of this line is m is 1 over e. So I now have a point on the line and I have the slope of the line. And so I can write the equation of the line, y minus y1 is equal to the slope 1 over e times x minus x of 1. Okay, and so that is the function, that is the equation of this line. Okay, and I can now go and plug in, instead of an e, I can throw in a 3, and that'll do everything for me. The thing that seems to get students hung up is that typically when they ask for linearization, they want you to write this as a function of x. So if you think of this as some linear function of x, just replace y with L of x minus 1 is equal to 1 over e times the quantity of x minus e. Basically, get this by itself. So L of x is equal to 1 over e times x minus e plus 1. Okay, and I could go ahead and distribute and all of that, but basically all I want to do is evaluate this thing at, excuse me, at e. I'm sorry. If I evaluate this thing at e, I should get 1. So if you put an e in there, this is 0, and 0 plus 1 is indeed 1. Okay, but I wanted to know the value of this thing at 3. So I'm basically interested in L of 3. So that would be 1 over e times 3 minus e plus 1. And so that would give me a pretty good estimate of the natural log of 3. And so I don't really see any easy way to really simplify this. I guess I could distribute that, and I would have 3 over e minus 1 plus 1, and that is equal to what? 3 over e. Okay, and so basically what we're saying is the natural log of 3 is roughly equal to 3 over e, and this is without a calculator. Okay, so I suppose I should have sat down here with a calculator. Okay, I don't know that I can share this screen with you or not. I think when I told it I was going to share a screen, I'm not sure if it was just the visualizer. Let's try this out here. And let's try 3 divided by e. I don't know if you guys can see that on your screen or not, but it tells me that this is equal to 1.1036. Okay, and if I also type in, okay, allow. Okay, if I type in the natural log of 3, okay, let's see what that says. That says the natural log of 3 is actually equal to 1.0986. So it's really not a bad approximation. And so then the question becomes, they almost always ask this in AP, is it an overestimate or is it an underestimate of the function? And so in this case, let's get back to the visualizer here. If I look at this function, the line is above this curved graph. This curve is concave down here. And so this is always going to be an over approximation. It's going to overestimate the true value of the natural log of 3. And sure enough, it did that. Okay. This is approximately 1/100th higher than this, 1.09, whereas this is 1.10. Okay. If you actually look at the decimals, it's not quite as bad as being off by 0.01. It's actually a little bit closer than that. But that's the idea of this. So that is what this is asking us to do is to estimate the natural log of 3 using linearization. So the natural log of 3 is approximately equal to 3 over e. I don't know why I wrote approximately equal to, and that is decimal approximation 1.1036. Okay. Alrighty, guys. I'll see you at the next video. I'm going to check that this video actually recorded the sound and I recorded the proper window and everything. Okay. So I'm going to tell it to stop sharing, and let's hope that this worked out. Okay. All right. Now I have to leave the call. Okay. Alrighty, guys. Take care. Bye-bye.